Dear learners, welcome to this interactive video lecture session. Today's topic is Statistical Process Control. This topic is from the 18th module of the course Quality Engineering and Management. I am Shubhashish Maji, professor in School of Engineering and Technology from Indira Gandhi National Open University. So, dear students, today's topic is Statistical Process Control. In short, we will call it SPC. After listening to this video lecture, you will be able to understand the Statistical Process Control. You will be able to know the assignable and random causes, and you will also be able to explain the normal distribution and central limit theorem. Statistical process control is concerned with establishing standards, monitoring standards, making measurement and taking corrective action as a product is being processed. All processes are subject to variation, and the key to achieve quality is keeping variation under control. SPC involves using statistical techniques to measure and analyze the variation in the processes. Statistical process control is used to monitor product quality and show progress in relation to the aim and targets. SPC can ensure that the product is being manufactured as designated and intended. Thus, SPC will not improve the poorly designed product but can be used to maintain the conformance of the product to its specifications. Often the term statistical quality control is used interchangeably with statistical process control. However, statistical quality control includes acceptance sampling as well as statistical process control. Both SPC and sampling plan utilize the connection between properties of a sample and properties of parent population. Acceptance sampling relies on accepting or rejecting a sample based on the number of defectives found and thus is chance based. SPC, on the other hand, provides the opportunity of correcting or tuning the production process in time to avoid batches being rejected later. The basis of SPC is a measurement performance over a fixed time. Samples of process outputs are examined by fixed intervals and real change in a process can be identified. If the samples are within acceptable limits, the process is permitted to continue. In such a situation, the process is said to be in statistical control. If the samples fall outside the limit, the process is stopped and the cause is located and removed. The simplest way of describing the performance of a process is by means of control charts. The pattern of data in a control chart enables to distinguish between common and special causes. Now you will come to know of constructing control charts for various data and of rules for recognize the existence of special causes of variation. Before that, it is essential to know about assignable and random causes. Walter Shewhart recognized in the 1920s that all processes are subject to certain degree of variability. Some processes display controlled variation while others display uncontrolled variation. A controlled variation is one which displays consistent pattern of variation. The causes of this variation are inherent in the process and occur by chance. They are called random or common causes. The variation due to such causes are natural and cannot be eliminated from the process. On the other hand, an uncontrolled variation displays patterns that change over time. The causes for such varying patterns can be assigned to special causes. Hence, such causes are called assignable causes. A variation caused by an assignable cause can be traced to a definite source. Both assignable and random causes affect the process quality, which in turn affects a product or service. The concept of assignable and random causes are illustrated through an example explained now. Figure shows the delivery time in minutes taken by a courier service agency operating in a city. The time between two consecutive trips varies throughout. However, shortened trip requires unusually less time, delivery by helicopter, or high time tire puncture. Thus, the events like accident on motorway, stop for speeding, express delivery, etc. are special or assignable causes. Otherwise, there is very little difference between the time between two trips. These smaller variations can be traced to random causes such as waiting in traffic or delay in starting of delivery van. There are countless minor factors that cause random variables. Now you see this graph and see that there is an average time mentioned, but sometimes the delivery is taking very less time, like delivery by helicopter. And nowadays you might have seen that the deliveries of the products and services to the customers are providing in a different way so that the delivery time will be less. But there are causes like accident on the subways, or there may be a tire puncture, or there may be a speeding car for which the traffic police may stop that passenger, or the motorist who is going to deliver the projects. Obviously, there will be delay in such situations, and those are known as the assignable variables. The purpose of statistical process control is to bring the process into a state of statistical control and improve its performance by assessing the consequence of variation caused due to assignable or random causes. There are two ways to improve a process. Number one, if a process is under control, variation, that is, variation due to random causes, is inherent. Then, unless the process is changed, it will continue to operate this way in the future. Hence, the process must be changed. If a process is affected by factors outside the process, then the variations introduce instability into the process and it becomes uncontrollable. The performance of service will fluctuate and become unpredictable. Since the cause of these variations are assignable, these causes once identified should be eliminated if bad and incorporated into process if good. Thus, it is essential to monitor the variations of a process throughout. The control charts are the most widely used tools to monitor a process. The control charts are based on the principles of normal distribution. As such, it is important for every process engineer to have a firm grasp of what a normal distribution is. Now we shall be discussing normal distribution in the context of SPC. The normal distribution is probably the most recognized and most widely used statistical distribution. The reason for this is that many physical, biological and social parameters obey the normal distribution. Such parameters are then said to behave normally, or more simply are said to be normal. Only two parameters are needed to describe a normal distribution, namely the mean or its center and the standard deviation, also known as sigma or its variability. The normal distribution is bell-shaped. It peaks at the center and tapers off outwardly while remaining symmetrical with respect to the center as shown in the figure. So this figure gives the normal distribution curve. You see that at the center the peak is there and the mean is situated at the center, and there is sigma, we call it standard deviation. We will talk about the significance of the properties, the sigma, in our later course of discussions for this lecture. The shapes of the normal curve depends on the value of the standard deviation. The notable feature about normal distribution is that regardless of their standard deviation value, the percentage of data falling under a given number of standard deviation is constant. For example, if the standard deviation of process 1 is 10 and the standard deviation of process 2 is 20, process 1 and 2 will have different data distribution sets, process 1 being more stable because it has less standard deviation, but for both processes 68% of the data under the normal curve will fall within plus minus 1 sigma from the mean, and 32% of the data will be outside it. The central limit theorem. The central limit theorem states that irrespective of the distribution of the individual readings, the sample mean are normally distributed with the same mean but narrower standard deviations than that of individual readings. To illustrate this concept, consider the situation of selecting sample of n items in random fashion from a population. Let the mean of this sample be mu1. Now, if we take a second random sample and found the means of this new sample, say mu2, then it is highly likely that the two sample means will have different values. In other words, it is more probable that mu1 is greater than mu2 or mu1 is less than mu2. This may seem worrying because as we take more samples, there will be more means like mu3, mu4 and so on. But the central limit theorem provides a helping hand. It says that if larger samples are taken, then it is more likely that the sample means will be closer to the actual population mean, that is mu. Any two sample means may be different, but they should still be close to the true mean. The theorem also states what distribution the sample means will have. The distribution sample means from any population tends to be a normal distribution as the sample size tends to infinity. The normal distribution has a variability given by standard deviation sigma. The variability in the sample distribution is given by standard error, we call it sigma x, and related to sigma by the relation, that is sigma x is equal to sigma by root n, where n is sample size. The variability in a sample distribution is best illustrated through a histogram. A histogram contains vertical bars of the sample statistics, say mean. For example, consider means from a population of 10,000 items with sigma equal to 2.897 as shown in the next figure. Now we randomly choose samples of size 2 and calculate the means. The resulting sample distribution is shown in the next figure B. The standard error becomes 2.897 divided by root 2 is equal to 2.043. If we further increase the size of individual samples to 10 and 50, the standard error further reduces to 2.897 by root 10, that comes out to be 0.917, and for the second case the standard error becomes 2.897 by root 50, that is equal to 0.41. Thus the variance of the sample distribution will be smaller than that of population sigma. Figure C and D show the sampling distribution of means for sample sizes 10 and 50 respectively. It is clear that as the sample size increases, the sampling distribution approximates the normal distribution curve and the variability decreases. Moreover, the reduction in variability is independent of the population. It depends only on the sample size. Now this is the fourth figure which were already mentioned. The first one, A, is histogram of populations, and second one is while taking n is equal to 2, the normal distribution, it is flattened, and for the third one we have taken n is equal to 10, sample size is more, and the last one is the n is equal to 50. So distribution of population and sampling distribution with various sizes. Now let us discuss the central limit theorem. The unique features of this theorem are as follows. Number one, the immediate advantage of central limit theorem is that there is no requirement to develop a separate statistical model for every non-normal distribution data. Number two, the distribution will approximate normal distribution even though the parent population from which the sample is chosen is not. Instead of taking the mean of entire population, which is a conversion process, one can observe the means of n samples and determine mean of entire population. Dear students, so far we have discussed about the statistical process control, and later on we will see how this statistical process control will help us for maintaining the quality of product or services. Let us summarize our discussions. We have discussed the statistical process control, we have discussed the assignable and random causes, and we have also discussed the normal distribution and central limit theorem. Thank you.